Alright, so this is the next video in our installment on complex numbers. We're still in section 2.1 for Math 1410, Spring 2017. In this video we're going to move on from the sort of general historical introduction that we gave last time and start actually working on the mathematical definition of complex numbers and how do you actually work with them, how do you do arithmetic, how do you add, multiply, and so on. So, as a reminder, let me maybe just squeeze this on the cover page where we've got some room. The complex numbers, C, are defined to be the set of all numbers of the form x plus iy, where x and y are real numbers, and I here is the square root of minus 1. So each complex number consists of two pieces. The number x, which is just an ordinary real number, and then the second term I times y. Now I itself is a real number, but it's being multiplied by this square root of minus 1, which is, seems like a bit of an odd duck at first, but we'll see as we go along that in some settings this makes perfect sense. So how do you add complex numbers? Well, you add them in some sense in the most obvious way possible. You just combine like terms. The same as if you were adding two polynomials or adding, as we'll see later on, adding two vectors. You just add the corresponding parts. So if I have two complex numbers, so I have a, say, z1, x1 plus I times y1. I have a z2, x2 plus I times y2, and I want to add them together. Well, I add the x's and I add the y's. Just to kind of, for ease of reference, I should note that if I give you z is equal to x plus I times y, we call x is sometimes denoted like this, re of z. This is called the real part, and y is sometimes denoted im of z. This is often referred to as the imaginary part. And so this terminology kind of dates back to 16th, 17th century, when people kind of refused to accept that there was such a thing as a complex number, and so they declared these things to be imaginary, as numbers that couldn't possibly actually exist. They were simply figments of people's mathematical imaginations. So with this language, one of the ways to describe addition of complex numbers is to say that, well, to add two complex numbers, you simply add the real parts and you add the imaginary parts. So if we want to do a few examples, if I want to take, say, 3 plus 4i, and I want to add, let's say, minus 5 plus 2i, I simply combine the real and the imaginary parts. So I say, okay, well, that's going to be 3 minus 5, and then I've got 4i plus 2i. So altogether, 3 minus 5 gives me minus 2. 4 plus 2 gives me 6. So I get minus 2 plus 6i. And of course, I could have something like, they don't have to be integers. I could have something like root 2 plus 1 half I, and I might want to add to that something like 1 plus 2/3 I. I can still work with that. The only trouble is, well, I can't actually simplify root 2 plus 1, and for 1 half plus 2/3, well, maybe we have to kind of go off on a bit of scrap paper. I'll do it up here in the corner and say, well, oh yeah, how do we do 1 half plus 2/3? That's going to be, let's see, 3/6 plus 4/6, and so that's 7 over 6. Okay, so 7 over 6 times I. And so again, we can put things together like that, and we can combine these. So anytime you want to add two complex numbers, you can combine them into a single complex number, and notice that the sum is once again of this same form, x plus iy, real part plus I times the imaginary part. Okay. Um, Now, this addition satisfies certain properties, and one of the things that you might notice if you watch the videos for chapter 1 is that these are exactly the same properties that the real number arithmetic satisfies for addition, right? So you have the commutative law, and the second one here says that addition is associative. And the third one says that 0 still acts as the identity element, and the fourth one says that if you define negatives in the obvious way, well, then you have inverses. And then, of course, once you have inverses with respect to addition, you can use those to define subtraction. So if I want to do subtraction, if I want to define z minus w, I define that as z plus minus w. So, for example, if I wanted to do 3 plus 4i and I wanted to subtract off 2 minus 5i, I would say, okay, well, that's 3 plus 4i. So I turn the subtraction into addition. The negative of 2 minus 5i, it's defined here. I just change the sign on both of the numbers, on both x and y. So the negative of 2 minus 2. The negative of minus 5, that double negative, gives me a plus 5i. And now I can combine those, right? 3 minus 2 gives me a 1. 4i plus 5i gives me 9i. Okay. Now, moving on to multiplication. Addition kind of works exactly the way you would expect it to. Multiplication, well, the formula looks kind of scary, right? I wrote this thing down here and it looks kind of awful, but it really is just, it's FOIL. It's FOIL. The only thing is that you have to remember that you're dealing with complex numbers, and complex numbers involve this I term, and I is the square root of minus 1. And if I is the square root of minus 1, that means that when you square it, you should get minus 1. So if you want, you can take this as a definition of multiplication. So the product z times w, if z is x plus iy and w is u plus iv, you can just take this last term here as the definition of multiplication. But I find it's better in practice to just kind of think of this as doing FOIL, where you have to remember that I squared is equal to minus 1. So for example, if I wanted to do 2 minus 3i and I wanted to multiply by 4 plus 5i, I just multiply out and expand. So I do 2 times 4 gives me 8, right? And then I do 2 times 5i. As you would expect, twice of 5 should give me 10. Then I do the inside terms, so minus 3i times 4, that minus 3 times 4 gives me minus 12, minus 12i. And then the last one I've got, so here's my last term right here. So I've got minus 3 times 5, so I've got minus 15, but then I've got an I times an I. I've got minus 15i squared. So this is 8 plus 10i minus 12i minus 15, but that I squared is minus 1. So minus 15 times minus 1 gives me a plus 15. So 8 plus 15 gives me 23. 10 minus 12 gives me minus 2i. Okay. And that's how we multiply complex numbers. Again, this might be a good point to stop and try a couple of exercises. Just you can even make up your own, plug in some numbers, multiply things out, or try ones from the textbook where you can look up the answers in the back. And once you've done 3 or 4 of them, you'll start to get the hang of it. And by the time you've done this, a dozen times, you'll be able to do it without even thinking. Okay. Now, Multiplication, by the way, satisfies most of the properties that you might expect it to, but it's not really clear that there are inverses. By the way, don't worry about writing. There's some scary looking stuff on this slide. Don't worry about writing it down. Can you divide? Are there inverses, right? With real numbers, we know that as long as our number is non-zero, we can divide by that number, right? We can define a multiplicative inverse by this usual relationship here. Can you do it for complex numbers? Well, I mean, one way to think about it is you just try to solve an equation, right? So you choose two complex numbers, right? Say Z, W, and you want them to satisfy this relationship. You want their product to be equal to 1. So I'm going to try to write the entries of W in terms of the entries of Z in such a way that the product is equal to 1. So I multiply things out using the rule for multiplication right here, and I set it equal to 1, remembering that 1 really means 1 plus 0 times I, right? 1 is technically a complex number, it's just the imaginary part is 0. That gives me a pair of equations. You can solve those equations. It's not very easy, but you can solve them. And you can figure out what u and v have to be in terms of x and y. And you get this formula down here for the reciprocal, right? So this w, this is 1 over z. Well, that doesn't seem like a very pleasant thing to try and memorize, and we certainly don't want to have to go through these steps every time to come up with it. So is there an easier way? Is there a simpler way to come up with this? Well, fortunately there is. You have to introduce a new gadget called the complex conjugate. So the complex conjugate is kind of a simple thing. All you do is you change the sign in front of the imaginary part. So instead of x plus iy, you do x minus iy. So the key difference is right here in that minus sign. So you're changing the sign in front of the imaginary part. Now you might remember that there are conjugates that come up when you deal with radicals in high school. So you might just as a refresher, if I give you something like 2 plus root 3, well, that has a conjugate. 2 minus root 3. And where did you use these conjugates? You used them when you were doing this, rationalizing, right? You said, okay, I want to do 1 over 2 plus root 3, and you said, okay, I multiply top and bottom by this conjugate 2 minus root 3, 2 minus root 3, and that allows you to simplify. You get that square root out of the denominator. Well, that's exactly what we're doing here. Remember that I is just the square root of minus 1, right? So the conjugate of x plus root minus 1 times y is just x minus root minus 1 times y. So you're doing the exact same thing. You're just changing the sign in front of the radical. The radical just happens to be the square root of a negative. But what's really useful here is that, if you're doing something like this guy up here, 2 plus root 3 times 2 minus root 3, that number, well, it's never going to come out to give you 0, but it could come out to be either positive or negative depending on the numbers that you're dealing with. One of the really nice things about the complex conjugate is that when you multiply a number by its conjugate, you never get a negative number. You always get a positive real number because z bar is x plus iy times x minus iy. So you have sort of a difference of squares thing going on here. You get x squared, then you get minus I xy, then you get plus I xy. Well, those are going to cancel. And your last term is I squared times y squared. Sorry, that comes with a minus sign, doesn't it? Because you've got iy times minus iy, so you get minus I squared. But we also know that minus I squared, that's minus minus 1, that's plus 1. So you get x squared plus y squared. So how do you divide by a complex number? How do you take the reciprocal? Well, you multiply top and bottom by the conjugate the same as you would have when you were rationalizing a radical. It comes out in exactly the same way. So you get the same result here, x minus iy over x squared plus y squared. You can see that that's the same thing that you have here, x minus I times y. Everything is divided by x squared plus y squared. Okay, so it works out exactly the same. All right, and once you introduce the complex conjugates, so that you can introduce reciprocals, then you find that complex multiplication satisfies exactly the same rules as multiplication for real numbers, right? So you still have the commutative law, you still have the associative law, you still have 1 as the identity. You still have an inverse for every non-zero element, and you can also check, and it's a little bit of work, we're not going to do it here, but you can check that the distributive property still holds over the complex numbers. And so the rules of algebra are still the same, and that means that when you're doing things like solving equations, trying to simplify, you can follow your instinct and assume that most of the rules that you're going to use for your algebra are going to work out the same as you expect them to. Okay, so that's where we'll stop for this video.